Hi, my name is Mark. I recently completed my master's in Dan Bernard's lab at McGill University in Montreal. Here I will present some highlights of our work, which is published in the April 2017 issue of Endocrinology. Loss-of-function mutations in the immunoglobulin superfamily member 1 gene, or IGSF1 gene, lead to a novel form of central hypothyroidism with or without macroorchidism and prolactinemia, collectively called IGSF1-deficiency syndrome. This syndrome is characterized by low to low normal circulating thyroid hormone levels in the presence of non-elevated TSH levels. From its high expressions in the brain and the pituitary, it appears that IGSF1 plays a role in the central control of the thyroid. However, the exact function of IGSF1 is still undefined. To study IGSF1 deficiency syndrome and the role of IGSF1 in the hypothalamus-pituitary-thyroid axis, we designed an IGSF1 loss-of-function mouse model using the recently described CRISPR-Cas9 technology. The mutation we introduced resembles many mutations found in IGSF1 deficient patients. Once we established that the mice do not express the normal IGSF1 protein, we began to characterize their phenotypes. At first, we were surprised to see that under normal laboratory conditions, the IGSF1 mutant mice showed normal circulating thyroid hormone and TSH levels. We quickly discovered, however, that their HPT axes were far from normal. Expression of the subunit genes that comprise TSH was reduced in the pituitaries of mutant mice relative to controls, as was the pituitary content of the TSH protein. Importantly, these mice also exhibited reduced expression of the TRH receptor, the brain peptide that stimulates TSH secretion. These results suggested to us that reduced TSH production may result from reduced TRH sensitivity in the pituitaries of the IGSF1 mutant mice. To test this idea, we challenged the mice using two complementary approaches. First, we injected exogenous TRH and examined the acute release of TSH, which we discovered was blunted in the mutant mice. Second, we increased endogenous TRH secretion by rendering animals severely hypothyroid with a low iodine diet and supplemented with propylthiouracil. Typically, this challenge, which reduces thyroid hormone negative feedback, leads to large increases in TSH secretion. This was true in our animals as well, but again, the response was significantly blunted in the mutant mice relative to controls. Collectively, our results indicate that IGSF1 deficiency leads to reduced pituitary sensitivity to TRH in mice. A similar phenotype may underlie central hypothyroidism in IGSF1 deficient patients. More work is needed to understand how IGSF1 regulates TRH receptor expression and how loss of IGSF1 leads to macroorchidism and low prolactin in some patients. Thank you for listening, and for more details about our work, you can access the April 2017 issue of Endocrinology. And to learn more about the Bernard Lab at McGill University, you can follow the links below.